Okay, I'm going to get started. I hope you can hear me okay. Today we're going to start our last module of the semester. And actually, this module really is about applying the laws of nature that we've met so far to some everyday situations. So we're going to be applying Newton's laws to everyday situations. We're going to be applying energy momentum conservation laws to some everyday situations. And that's what the remaining classes will be about. So we're going to explore a number of different things by applying Newton's laws and conservation laws. We'll actually go from the very top of the atmosphere, applying laws there, to the very bottom of the oceans, applying the laws there, and all sorts of places in between. In today's class, we're going to explore some selected interesting properties of solids. And we'll see how by exploring those selected interesting properties of solids, we actually get a glimpse. We're actually able to see the atoms within the materials, the atoms and molecules within the materials, and the interactions between the atoms and molecules in the materials. We'll then move on to, in next class and the following classes, exploring some selected interesting properties of fluids. And again, there we'll see that we'll get a glimpse at, or we'll be in a way able to see the atoms or the molecules within inside the fluids and the interactions between the atoms and molecules within inside the fluids. And then the very last topic that we'll cover in the last two lectures of the course will be to turn to a type of motion that we call periodic motion. So it's sort of oscillatory motion. It's a sort of repetitive motion. And we're going to explore that type of motion. We're going to learn from that type of motion how we can make precision measurements of time. And we're going to return to finally to the concept of time, which we introduced in the very first lecture class when we talked about the fundamental dimensions of nature. So today's class is about this language of deforming matter, of deforming materials like steel rods, like plastic rods as examples. And we're going to introduce this language of stress, strain, elasticity, and strength. We're going to model the steel rod or the plastic rod or a steel wire or a copper wire. We're going to model those materials as springs, as actually a little collection or assembly of atomic and molecular springs. And so we're going to do that. We're going to introduce this language, introduce these concepts of stress, strain, elasticity, and strength. We'll look at some illustrations of deformation. And the illustration I'm going to look at is the stretching of an elevator cable. That's kind of an interesting problem to look at for deformation of solids. That happens for elevator cables. They do get stretched. And we're going to explore cases where the stretches are larger, cases where the stretches are smaller. Okay. So let me begin just by a reminder about springs and spring forces. And so I've tried to sketch that out here. So if you remember, many classes ago, we introduced the force that's exerted by a spring when you compress a spring or when you stretch a spring. So that was the spring force. In this top little picture here, I've got to get my annotation working again here. In this little picture, the spring is at equilibrium length. So it's neither stretched nor compressed. it's exerting no force on us. If you compress the spring, by the way, I'm having to draw these arrows with my mouse, not with my drawing pad, because my drawing pad is not working. My mouse is still working. So the drawing in today's class is going to be pretty bad drawing. I think that I would expect better of a 2 or a 3-year-old. But anyway, this second sketch here is where I've compressed the spring. So I exerted a force to the left on the spring. That's pictured in magenta there. That's the force labeled F. And the force of the spring that's pushing back on me is the spring force in blue there, F subscript F. And so that's the spring force. My force and the spring force are kind of a pair of forces, action and reaction forces. But we think of the spring force as being the force that the spring is exerting in that pair. And as we know for the spring force, the more we compress the spring, then the larger the force. So the larger X, the larger the compression, the larger this force. And also that if I compress the spring over to the left, the force is back towards the right. So that's the spring force. And the same business if I stretch the spring. Here we are. Bottom plot. If I stretch the spring by pulling it to the right, that's my force in magenta that's labeled F towards the right. The spring pulls back towards the left. That's the blue force, F subscript S, towards the left. And so again, the spring is trying to pull back towards the equilibrium length. And the more I would pull the spring towards the right, then the greater the spring force that's acting towards the left. And all that understanding of how springs work is encoded in this spring force law, that the force is in proportion to the distance you've compressed or stretched the spring from equilibrium times the spring constant, which characterize whether this is a spring that's easy or hard to stretch, with a minus size that says that if you compress, the spring always tries to stretch itself out. If you stretch the spring, it will try and compress itself back to the equilibrium length. So that's how the spring force works. So that's just a reminder. Okay, so our idea or our model for understanding the deformation of solids is going to be the following idea or model. And just to be concrete, let's imagine that we've got a solid steel rod. So upstairs here in this slide, here's the solid steel rod. And we're going to think about stretching and compressing it. And downstairs here, if I was to look inside the solid steel rod with my microscope, I would see all the atoms and molecules of the steel rod. And so that's pictured on this little view here. In magenta are the atoms and molecules of the steel rod or the plastic rod or the aluminum rod. And these springs, they're not little real springs sitting inside the steel rod. Those are my model of the interaction between the atoms and molecules of the steel rod. And they're an approximation of the interactions between the atoms and molecules of the steel rod. Okay, so that's going to be our model. And let's just walk through some features of our model. So supposing I'm neither compressing nor stretching the steel rod, and the steel rod is at its equilibrium length. It's neither stretched nor compressed. The atoms inside the steel rod, or the molecules inside the steel rod, if I could peer into that steel rod, they would be at their equilibrium separations, their natural separations between one another. So that's when you're neither compressing nor stretching the steel rod. Supposing I compress the steel rod. So if I compress that steel rod, then I'm going to be not only just compressing the steel rod, but microscopically, I'm squeezing together, compressing together the atoms, molecules that make up the steel rod. And when you compress together the atoms and molecules that make up the steel rod, these interatomic forces between the atoms and molecules push back. They oppose that compression. They resist that compression. The atoms and molecules repel one another through this interatomic molecular force. And so in that way, when you compress the steel rod, it acts like a spring because it pushes back. And actually, the harder you squeeze the steel rod, the more it pushes back. So it acts exactly like a spring. You get a greater spring force from the steel rod, the more you try and compress the spring rod, the steel rod. So the same thing would happen if I tried to stretch that steel rod. If I stretch the steel rod, I'm pulling apart the atoms and molecules inside the steel rod. And the interactions, the atomic molecular interactions between, or forces between those atoms and molecules of the steel rod will pull back towards the equilibrium separation. And so as I try and pull or stretch the steel rod is pulling back because inside the steel rod, I'm trying to pull apart the atoms and molecules of the steel rod, and they're pulling back towards their natural equilibrium separation. They're attracting one another. And so that too is exactly like a spring. If I pull about the windings of the spring, it pulls back. If I stretch the length of the steel rod, it's pulling back. And actually, the harder I pull on the steel rod to stretch it, the harder it pulls back. So it's exactly like a spring. So this is the key point. This is the important point, that here it is. Sorry about how ugly that is, but the steel rod behaves from the point of view of deforming the steel rod and stretching and compressing the steel rod just like a spring. And it pushes back if I try and compress it. It pulls back if I try and stretch it. And the more I try and compress it, or the more I try and stretch it, the greater pushes or pulls it exerts to try and return itself, to return the length of the rod to the equilibrium length. Okay, so here now is my macroscopic picture of me deforming a steel rod. So in the top picture, this is the steel rod at its natural length, its equilibrium length. So this is equilibrium. And now I'm going to compress the steel rod. So I'm pushing from the right towards the left. That's the magenta force F. That's me pushing. And the steel rod is now pushing back with a force, with an opposing force. That's the blue F subscript F. That's the steel rod's force. If I do the reverse, right, I try and stretch the steel rod. If I stretch the steel rod, I'm going to pull the steel rod, the right-hand end of it towards the right. That's my force in magenta, labeled F. The steel rod pulls back towards the left with a steel rod force. That's this F subscript S in blue. And so that's our model now of how the steel rod behaves, acts when you stretch or compress it. At the microscopic level, so imagine you got these fantastic glasses now, the super microscope. At the microscopic level, if we could peer at the atoms and molecules of the steel rod and their interactions between one another, between neighboring molecules or atoms, then this is what we'd see. If the steel rod's at its equilibrium length, which is what I've pictured here, there's the equilibrium distance between the atoms and molecules inside the steel rod. If the steel rod is compressed, I'm compressing it here with my force in magenta towards the left. I'm compressing the atoms and molecules, and the interatomic, intermolecular forces are pushing back towards the right. And so that's the microscopic origin of the steel rod's force when we compress it. And likewise, if I stretch the steel rod, that's this bottom picture here, then I'm pulling apart the atoms and molecules from their equilibrium separations. And again, you get interatomic, intermolecular forces that, that pull back. And so as I pull the, as I stretch the rod here, I'm stretching apart the atoms and molecules, and there are interatomic molecular forces that are pulling back. That's this steel rod force here. And so that's our picture of deformation. Okay, so one thing that picture tells us, which is quite interesting, is actually the origins of two forces that we've been talking about over the entire semester. One is the tension force, and we work with that a lot. The other one is the normal force, and we've worked with that a lot. And this picture of stretching, compressing matter, deforming matter, gives us a clue, an understanding of the origins of those tension normal forces. So take a look at this sketch over here on the left-hand side. Here I'm trying to picture the origin of tension force. So I've got an apple, here it is, and I've hung it from a cable or a wire or a string. The downwards force of gravity on the apple is stretching the string, stretching the cable, stretching the wire. So it's pulling apart the atoms and molecules of the string, the cable or wire. And those atoms and molecules pull back through this interatomic, intermolecular force. And that's the origin of the tension force. So that tension force is coming about because I'm stretching the matter that comprises the string, the atoms and molecules that are making up the string. Over here on the left, no, this is the right, sorry. Over here on the right, I've got the apple now sitting on the table. Apple's sitting on the table. The apple is pulled downwards again by the force of gravity. That compresses the table. It's compressing the atoms and molecules of the table. It's pushing together more closely the atoms and molecules of the table, and they push back with their interatomic, intermolecular forces, and that's the origin of the normal force. And so what we've done here with our little model of deforming solids is, and that deformation arising from the atoms and molecules and the pushing together or pulling apart of the atoms and molecules, is explained where the tension force came from, is explaining where the normal force comes from. So it's a big breakthrough. And this deformation, this what we'll call elasticity of materials, as Lady Gaga is saying on this slide, is a real insight into, a real window into the interactions, the atomic molecular interactions between the atoms and molecules that are the basic building blocks of all the materials, like the steel rod or anything else. Okay, so now I want to get on to, we've developed the model. I want to get on to the language that we use for deformation. There's some technical language that we use for deformation that we'll work with when solving problems about deformation of solids. And the terms are stress, so we're going to have to learn what that is. Strain, we're going to learn what that is. Elasticity, what that is. And strength, what that is in this physics context, in this context of deforming solids. Okay, so let me just make a point here. As I say, we've modeled the deformation of solids on the stretching, compressing of springs. Now, springs, I always think of as they're owned by physics, right? Here at UK, all the springs are in the physics department. Rods, wires, cables, they're owned by the engineers. All the rods, wires, and cables are in the engineering department. And although we model the deformation of rods and wires and cables on the stretching, the compressing of springs, we do use a bit different language for the deformation of rods and wires compared to the stretching, compressing of springs. And so it's really that language of stresses and strains and elasticities, which is more of an engineering language, that we're going to layer on top of the original physics language of forces and displacements and spring constants. And so that's what this slide is about. On the left-hand side of this slide is the compression of, or the stretching of a spring in terms of the familiar language that we apply a stretch to the spring. In that case, creates a spring force. And we have a spring constant that describes whether it was easy to stretch or hard to stretch the spring. And then over here on the right-hand side, where we're stretching or compressing the rod or the wire, this is the new language that we're going to learn. And so when compressing or stretching a rod, we normally think of let's think about the geometry of the rod. So here's the length of the rod, L, and downstairs here, this would be the cross-sectional area of the rod. We call that A, not a very good A, sorry. And the deformation of the rod is expressed in terms of what causes the deformation. It's the force divided by the area that we call stress. The resulting deformation, that's the elongation, the change in length, delta L, divided by the original length. We call that the strain. And instead of a spring constant, we had a spring constant over here in the physics description that said whether the spring was easy or hard to stretch. We've got a elasticity constant. It's this Y here that tells you whether the rod, a plastic rod or a steel rod, is hard or easy to stretch. And for stretching or compressing, this constant is actually, specifically, it's called the Young's modulus. And it parallels the role of the spring constant. In both cases, they're kind of reflecting the elasticity or the rigidity of either the spring or the wire. If the Young's modulus is a small number, it's easy to stretch that wire. If the Young's modulus is a large number, it's very hard to stretch that wire. Just like if the spring constant was large, it's hard to stretch the spring. If the spring constant is small, it's easy to stretch the spring. So it's just a little bit different language that is more of an engineering language, less of a physics language. Let me point out a couple of features about what I would call the geometry dependence of the stretching or the compression, what we call the elongation of, say, a steel rod or say a plastic rod or an aluminium wire or a copper wire. So that's what this slide is about, how the elongation, that's the delta L, depends on the rod's geometry, which would be its length and its cross-sectional area. That's the L and the A. And so there's two remarks I'm making about it. There's one on the left, which is that the elongation is proportional to the length. And this one on the right, which is that the elongation is in inverse proportion to the area. So those two things mean the following. So compare, let's start on the left. Supposing you had a short wire and a long wire that are otherwise the same, i.e. they have the same materials, they have the same cross-sectional areas. And we're going to apply the same stress, to the short wire and the long wire. Well, if you apply the same stress, here it is, the stress, to the short and the long wire, and they're made of the same material, their elasticity is the same, then the longer wire, the one with a greater L, must elongate more. The delta L must be more. The shorter wire with the smaller L must elongate less. Delta L must be smaller. And so that reasoning comes out of this relationship between the stress, strain, and the elasticity. And it's simply, maybe it's an obvious thing, right? That if you've got same material wires, same cross-section wires, same stress on the wires, the long wire will stretch more, elongate more. The short wire will stretch less, elongate less. And so that's this statement here. That's this conclusion here. Okay, so this second situation over here says that the elongation of the wire is in proportion to the cross-sectional area, inverse proportion to the cross-sectional area of the wire. So let's see how that works. Again, let's think about this stress, strain, elasticity relationship. And we're going to imagine this time, instead of a long wire and a short wire, we're going to think about a thin wire, small cross-section, and a thick wire, large cross-section. But otherwise, everything is the same. We're going to apply the same force to these wires. So the force is going to be the same. These wires are going to have the same length, and they're going to be made of the same material. So all those things the same. This is the same. The force, the length is the same, and the elasticity, Young's modulus, is the same. Well, what does that mean for the elongation? What it means there is that if the area, the cross-sectional area of the wire is large, sits in the denominator over here on the left, it's going to make the elongation, the stretch, small. If the area is small, sits in the denominator on the left, it's going to make the elongation, the delta L, large. And so we can conclude that the elongation of a wire or a rod or a cable is in inverse proportion to its area. So these are the two important geometrical features of when you apply stresses and when you get strains, how the elongation resulting from the stress depends on the length of the rod and the cross section of the rod. It's in proportion to the length of the rod, inverse proportion to the cross section of the rod. And that does just make common sense, right? If you've got a long, small cross-section wire, and you put a weight on it, it's going to stretch a lot. If you've got a short, large diameter, large cross-section wire, you put a weight on it, same weight on it, it's going to barely stretch at all. So that's the geometrical dependence of the elongation on the length and the cross-section, those two geometrical parameters that would describe a rod or a wire or a cable. Okay. Often, if you ever go over to the engineering library, I wouldn't recommend it, but if you ever did, there are books and books of stress strain graphs. That's how they describe materials, with these stress strain graphs. It's how you know what materials to use when you're constructing a bridge or apartment buildings or whatever, from these stress strain graphs. So here's an example of a stress strain graph, and it gives us a little deeper understanding of that stress strain relationship from that formula that I described. So on a stress strain graph, it's hard for me to say for some reason, horizontally we've got strain, and vertically we got stress. So if you remember, stress is the force divided by the area of the thing you're stretching or compressing. So this is the stress is the cause of the deformation. And then the strain, if you remember that's the elongation, the delta L divided by the length of the rod or the cable or the wire that you're stretching. So this is the result. So we got the cause vertically and the result horizontally. I actually don't know why the engineers do it that way around. I have no idea about that, because in physics we'd always put the cause on the horizontal axis. It's the thing you do to the wire, and the result on the vertical axis is the consequence for the wire. Anyway, so that stress-strain relationship that we talked about, that the stress is equal to the strain times the elasticity, this equation here, that corresponds to a straight line on this graph, this green straight line here. So the more you stress the wire, the more the wire strains. The less you stress the wire, the less the wire strains. If you had a wire, let's look at dependence on the elasticity. If you had a steel wire, which is hard to stretch or strain, it has a big elasticity, a big Young's modulus, then you need a large stress to resulting in a small strain. And so this green line would be steep. And the Young's modulus is really the steepness of this line. If you had a nylon wire, right, that's much easier to stretch. So in that case, a much smaller stress will cause a much larger strain. And this line here would be much shallower because the Young's modulus or the elasticity would be different. Okay, so that's this green line is the stress-strain elasticity relationship that we've talked about. Now, there's a very interesting thing about materials that if you exceed a certain size stress strain, that model of the stretching or compressing of the material as stretching or compressing of a spring actually collapses, breaks down. And you no longer get that relationship between the stress and the strain. So if you look in this region here, right, the formula doesn't work. So the stress-strain relationship and the stress-strain elasticity relationship works when you're not compressing or stretching the steel rod too much, when you're not compressing or stretching the nylon wire too much. If you stress-strain them too much, then the formula breaks down. You don't get a straight line anymore. And finally, this is where you break something. I've broken a few things in my time, and this is where you break it. At that point, you've snapped the nylon wire, or you've snapped the steel wire. You've applied too much strain, and those little inner atomic, intermolecular forces couldn't resist that strain, that stress, and you break the nylon wire, or you break the steel wire. So that's a stress strain graph. Let me just make one more comment about it. So there are actually lots of different categories or lots of different types of strain. So let me just try and show you that with a little demonstration. I've actually got the demonstrations in my office today, so I'm just going to stop sharing this if I can. Okay. So remember what we're doing is modeling a steel wire or a steel rod or a nylon wire, or nylon rod as a spring. And so that's this idea that, look, here's a spring. As I stretch it, it pulls back. And this is a pretty easy spring to stretch. And so it has a small spring constant. Here's a spring, right? That, again, I can stretch this spring, but I'm not very strong, and it's really hard to stretch this spring. So this has a spring constant that is large. And so, you know, this is a sort of model of a nylon wire or thread that's easy to stretch from its natural equilibrium length. And this might be a model of a steel wire that's very hard to stretch from its equilibrium length. I can't do it. I've got no muscles, but anyway. Now, we're applying it to this. This is a piece of plastic that I got when I had physical therapy because I fell off my bike. And we're imagining this as a little collection of inner atomic, intermolecular springs, and I'm stretching or compressing those springs. So if we could peer inside here, when I stretch it, you can see I can stretch it a little bit. I remember doing this therapy, and I'm stretching apart those atoms and molecules. And you can compress this a little bit. It's kind of hard, but I can compress it a little bit. And again, you're pushing together those atoms or molecules. So you're either compressing the little atomic molecular springs or stretching apart the inner atomic molecular springs. Now, those are actually two types of deformations: compression and stretching. And we often call this a compression stress. If I try and push it together, I don't know whether it looks like I'm doing anything actually. And we call this a tensile stress when I try and pull it apart. But there's lots of other types of stretches. Look, here's another one. This is kind of a bending stress, right? Again, I'm deforming the atoms and molecules, pulling apart, pushing together the atoms and molecules that make up this material. Another one would be a twist stress. So here I'm twisting it. Again, I'm pulling apart, pushing together the atoms and molecules that make up this material. I really feel like I'm back in physical therapy now. Now, here's a steel beam. So this also has uh, tensile, we can apply tensile stresses, compression stresses, twist stresses, bend stresses, but its little atomic molecular springs are much stronger. They're a reflection of the steel material and its internal structure compared to the nylon or plastic material and its internal structure. So by comparison, I can barely stretch this steel beam and barely compress this steel beam. And it's very hard for me to twist it. Look, I'm very strong, so I can twist it a bit. And it's very hard for me to bend it. I can bend it a little bit. Okay. I'm sorry, that's all the demonstrations I have for today. This class does not come with many demonstrations. So it's a largely demonstration-free class. But the next classes, we got some, just to get you a little excited, we got some really good demonstrations. Okay, so again, if you were over in the engineering library, God forbid, there would be tables of elasticities and strengths of different materials. So this table, just to give you an example here, is tables of, we're imagining that we're stretching or compressing rods of aluminium or copper or steel or whatever. And we're looking at the values of the Young's modulus that determines whether it's easy or hard to stretch those materials. Modulus is a big number, then it means it's very hard to stretch or compress that material. And if it's a small number, it's much easier to stretch and compress that material. I got to get my annotation working again. So let me just make a few comments on here if I'm capable. Okay, so let's look at this guy, that's bone, and look at this guy, that's tendon. So you guys are all going to be doctors or physical therapists or physician's assistants or dentists. And so you know much more about bone and tendon than me. But I know I have bones and tendons. And I know that bones provide the rigidity and tendons provide a kind of elasticity in connecting, you know, muscles to bones. And so in our bodies, we want both rigid materials and we want elastic materials. And bones are our rigid materials and tendons are our elastic materials. And just look at the difference, these natural materials of our bodies between the rigidity, the Young's modulus of the bone, and the elasticity of the tendon. They're different by a factor of 1,000. So, you know, whatever evolution happened and resulted in us, you know, our bodies are made of some materials that are, you know, wildly different and appropriately designed for what we need, for the rigidity of the bones, for the flexibility of the tendons. When we build things, when humankind builds buildings or cars or boats or whatever, right? We want all sorts of different materials. So we kind of copy this evolution. And here's a couple of interesting materials. There's steel and rubber. And I think of these steel and rubber as kind of the man-made equivalents for our bone and tendon. The steel is very rigid, right? It has a very large Young's modulus. the rubber is very elastic, very small Young's modulus. And these guys, you look at these guys, these are different by 1,000,000-fold rather than 1,000-fold between the bone and the tendon. Okay, so that's just the world of elasticities, the table of elasticities. Let me show you one more table. And this is a table of strengths. So if you remember, if we pulled too hard on the steel wire, we would snap it. If we push too hard on a nylon rod, you'll snap it. And the stresses, the maximum stresses that the nylon rod will break at, or the steel rod will break at, if they're compression stresses, then the maximum stress is called the compressive strength. And that's over on the right on this table. And if you're stretching your steel rod or your nylon rod, then the maximum stress before it breaks is the tensile strength. So these numbers are, they're not the elasticities of materials that tell you how easy or hard it is to stretch, but they tell you about the breaking, the snapping of the materials when you stretch it or compress it. And as I say, for compression, we use the word compressive strength. For stretching, we use this word tensile strength. I don't know the reason for that at all. And so let's just compare a couple of quantities here: steel, a couple of materials here, brick. We use steel and brick in building buildings. We might typically use, brick if we build a house. We would use steel if we build a skyscraper. And one of the reasons for that is that to do with the strengths of these materials under which they will break. And you'll notice one thing about brick here, that it's pretty strong under compression, which is what you want because you're putting brick on top of brick on top of brick. So you're compressing the bricks with other bricks. It's not so strong in terms of stretching. This is a much, much smaller number. And so stretching, bricks have the interesting characteristic, they have this interesting property that they're strong when you try and compress them, which is what you want for building something, but they're weak when you try and stretch them. So, if the building tips over, they might break because they're getting stretched apart. Okay. Well, that's all the language then. So we've done. Okay, I think we've wrapped up the quiz. So this is a quiz that asks us to compare the elongation of two jungle vines with two identical spherical tarsons hanging from the two jungle vines. So the vines have the same materials, their Young's modulus is the same. The vines have the same cross sections, so A is the same. The two tarsons are identical, so the forces on the vines are the same. But the length of vine A is twice the length of vine B. So let's just go through that. That's the force, F is the same, A is the same, Y is the same. Only the length is different. And so this is a question about, how the elongation depends on the geometry, specifically how the elongation depends on the length. And we talked about this earlier when we talked about the stress-strain elasticity relationship. If the stress is the same, if the lengths are, the Young's modulus are the same, then the longer vine will stretch more, the shorter vine will stretch less. So vine A elongates more. Okay, so let's look at a few examples of calculations involving stress, strain, elasticity. Um, so in this calculation, we see a mine elevator. And in a mine elevator, you know, you have this, uh, you have the elevator that's supported by a long cable that's wound around a drum. And, you know, you go down the mine by unwinding the cable, and you come back up the mine by winding back up the cable. And we're told that in this case, the mine elevator has a mass 670 kilograms. The steel cable has a diameter that's 2.5 centimeters. So it's like an inch cable, inch diameter cable. And we're asked to figure out how much that cable is stretched when the elevator's near the top of the mine shaft, 12 meters cable above it. When it's near the bottom of the mine shaft, 450 meters of cable above it. And, you know, we've already looked at the quiz question. We know because it's the same steel cable with the same Young's modulus that when there's the same stress on it, when it's short and when it's long, it's going to elongate more when it's long and elongate less when it's short. But we're going to quantify that. And so here I'm going to do the calculation. And I'm going to do it first for this case. It's at the top of the mine shaft, hanging on 12 meters of cable. And so I always want to draw, you know, this is an application of Newton's laws, basically. And so we draw a picture showing the forces. In the center here, this is the elevator. Upstairs here, this is the cable. And to that picture, I've added a diagram of forces. So the elevator is pulled down by gravity. This is the force of gravity on the 760 kilogram mass elevator. And in green here, that's force of gravity. And then in red here is supported by a tension force from the cable. And if it's just hanging on the cable, then that tension force must exactly balance that gravitational force. The tension force will be 6,566 newtons because the force of gravity was 6,566 newtons. So you end up with zero net force, and the elevator is just hanging there. So that's, as I say, this is simply all this stuff from this module is applications of old stuff about forces and energy. Okay, I wrote down a couple of numbers here that I either got from the problem that the diameter was 2.5 centimeters. If you work out the cross-sectional area, that's 5 times 10 to the minus 4 square meters. And then I looked up in my table for steel, the elasticity, the Young's modulus appropriate to stretching the steel cable. And then I went to our understanding of the relationship between stress, the cause of deformation of the cable, strain, the resulting deformation of the cable, and the elasticity that describes whether the cable is easy or hard to stretch. So it's this relationship here. I wrote it slightly differently organized here, but it's that stress, strain, elasticity relationship. For this problem, I filled in the definitions of stress, force over area, the definitions of strain, elongation over length. And then I just rearranged for the quantity that I'm after. That's the elongation here. In terms of all these other quantities, force, length, area, Young's modulus, I know them all, right? I know the force on the cable is that weight of the elevator. And then I know the dimensions of the cable, its length, 12 meters, and its cross-sectional area, 5 times 10 to the minus 4 meters squared, and its elasticity, this number here. And if you plug them all in, That cable only stretches, it's barely a millimeter stretch for that 12-meter long cable. Imagine 12 meters, 1 millimeter is a small stretch. Okay. So we have to do the same thing. That was at the top of the mine shaft. Now let's take a trip. Let's go down to the bottom of the mine shaft. Are we worried about the elongation of the cable at the bottom of the mine shaft? So the calculation is the same procedure. So I'll just go through it very quickly now. We've now all we changed is the length of the cable. It's now 450 meters. We've still got the situation where if we think about the elevator, it's being pulled down by the force of gravity in green here. It's being pulled up by the tension force in red here, so that the net force on the elevator is 0 here. We still have a cable that has an area of 5 times 10 to the minus 4 square meters. We still have the same steel cable with this Young's modulus. And we've still, of course, got the same physical relationship modeled on the cable being a collection of springs between the stress causing the elongation, the strain measuring the elongation, and the elasticity that tells you how easy it is or hard it is to elongate it. And again, I just fill in the definition of stress, fill in the definition of strain in terms of forces and elongations. And I rearrange for the quantity we want, the elongation in terms of the quantities we know, fill in the numbers. We know the tension force in the cable, we know the length and cross-section of the cable, we know the elasticity. I get 30 millimeters. So at the bottom of the incline, right, the cable is now stretched more than an inch. And so with a really long mine shaft, you have to be cognizant, you have to be aware that that cable will stretch as the elevator goes down. You don't want the elevator clunking into the bottom of the mine shaft because you forgot to account for the stretching of the cable as the elevator went down the mine shaft. You wouldn't want to make an elevator cable for a mine shaft out of nylon or tendons because those stretch a lot and you would misjudge where the bottom of the mine shaft is. Okay, second example. So in this example, we're going to start worrying a little bit. I'm kind of a worrier about when the cable might break. So the question here is that the elevator is now down at the bottom of the mine shaft. I'm looking for the time because I have no idea. And maybe I've been talking for 3 hours and everybody's gone. The elevator is down at the bottom of the mine shaft. And we're going to consider, so if you move the elevator, that involves accelerating the elevator. And you might consider the case of, accelerating it upwards so that it can come back up again, or accelerating it downwards so that it can go further down the mine shaft. And the question here is really, well, we found that the cable had stretched by 30 millimeters when it was just hanging near the bottom of the mine shaft. But how much does the cable stretch if you try and accelerate the elevator upwards or accelerate the elevator downwards? And we're going to imagine accelerating 2 meters per second squared upwards, do that calculation, accelerating at 2 meters per second squared downwards, do that calculation. Okay, so this slide is my solution to the stretch of the cable when it's at the bottom of the mine shaft and when we're going to accelerate the elevator back up. And so again, start with a sketch of all the forces involved on the elevator. And here there's an important point. Here there's the key point. So of course there's still the force of gravity downwards. So that's the 6,566 newtons we worked out earlier on. But now the net force is no longer zero, and the tension force is no longer equal to the weight. Rather, the net force must be accelerating the elevator upwards, which means that there must be a greater tension upwards than the weight downwards. And so that tension force, I call it F here, must just not only counteract the weight, 6,566 newtons, but must additionally provide the acceleration, provide an extra force, ma, to cause the acceleration. And so in this situation where we're going to have a net acceleration and a net force on the elevator, it's here, the tension force must exceed the weight by that ma. And so if you calculate, you know the m, you know the weight, you know the a, you can calculate the tension force. It's now 7,910 newtons. So that's really the change when you're accelerating upwards. And you accelerate upwards when you want to return to the surface, right? You want to go home. Well, so now let's go ahead and do the calculation. Remember, I know the cross-sectional area of the cable. I know the elasticity of the steel cable. So I can go back to my stress-strain elasticity relationship. I can fill in the relationship of the stress to the force, the elongation to the strain, and then I can rearrange for the elongation in terms of all these quantities, the force, the length, the area, the modulus, Young's modulus that I know. And so I plug them all in, and what we find out is when the elevator accelerates upwards from the bottom of the mine shaft, the cable is stretched a little bit more because the tension in the cable is a little bit more. And so that stretch is 3.6 centimeters. It was 3.0 centimeters when the cable was just, the elevator was just hanging there. I just noticed, I don't know why I did this, but there's a question from Sarah, is the area pi r squared? But since instead of radius, you have divided by 4 because use diameter. Yeah, that's exactly right. So the equation for the area of a circle is pi r squared or pi d squared over 4. Okay, so that's accelerating upwards. We stretch the cable a bit more. And you might guess then that accelerating downwards, let's do that one next really quickly. Here it is. We might guess that we might stretch the cable a little bit less. So that the downwards acceleration, the downwards acceleration would be if we were in the elevator, we're near the bottom of the mine shaft, and we want to start going deeper, right, into the mine shaft. So let me draw that picture here. Again, sorry about the using a mouse today. Here's a diagram of the forces. So I want to emphasize all this stuff in this final module is about using the notions of forces and energy we've met earlier on. The elevator has a force of gravity pulling it downwards. It's going to accelerate downwards. And so to accelerate downwards, the tension force must be smaller than the force of gravity so that there is a net force that provides this acceleration. And so the difference between the weight and the tension force must be ma, or the tension force must be the weight less ma. That's how we ensure that there's an acceleration downwards. And so since, again, we know the weight, we know the mass, we know the acceleration, plug all those numbers in, and now the force in the cable, tension force in the cable is smaller than when the elevator was just sitting there. So it's 5,200 newtons. And then we can just work through the same procedure. I'm tired of saying this every time. Relationship between stress, strain, and elasticity. We can fill in the relationship between force and stress, between elongation and strain. We can solve for the elongation in terms of the things we know, which are the force on the cable, in the cable, and the geometry of the cable, its length, its area, and its material, its elasticity. And if you do all that, this is a mistake. Okay, I'm going to correct this. This should be 2.4, I think, centimeters. That's the amount that the cable now stretches. Okay, so that's interesting to know. Next time you're in Patterson Office Tower, and you're kind of worrying that the cable might break in the elevator, you know, that's like a mine shaft and it's a long cable and it is stretching. When you're worried about the cable breaking, worry most when you're going to accelerate upwards, because the cable, the tension is higher, the stress is higher, and the elongation is more. And worry less when you're accelerating downwards, because there the stress is smaller, the elongation is smaller, and the chance of snapping is smaller. Okay, I got one last example. I'll do this quickly because I've only got a couple of minutes here. And it's the example of the strength of the cable. That is, when will the cable snap? When will the cable break? So we better know this. And we figured out from the last two examples, right, where we had the the elevator hanging at rest and then accelerating up, accelerating downwards, that the most dangerous situation for being in an elevator is when you're accelerating upwards, because that's when the biggest stresses are in the elevator cable. And so we're going to imagine that our our elevator is going to accelerate upwards at 2 meters per second squared. I took this number from Patterson Office Tower accelerations, actually, and we're going to figure out the maximum mass of the elevator and the its occupants. We pile in more people to increase the mass. What's the maximum mass of the elevator and occupants before that Patterson Office Tower cable is going to snap on us? Okay, so again, I drew a picture. I'll go through that quite quickly, I think. It's this picture I drew before, where there's the weight acting downwards on the elevator, and there's the tension force acting upwards on the elevator, but the tension exceeds the weight because we've got to arrange for the upwards acceleration. So the tension exceeds the weight by MA. Now, we know we got a steel cable. It's the same type of steel cable in Patterson Office Tower. And I looked up the maximum stress that cable can withstand before it snaps. It's this number here. So we're no longer caring about, you know, that elasticity and the little stretching or bigger stretching of the cable. We're worried about now when this thing's going to snap and break on us. So that's the maximum stress. And so we want to calculate the maximum stress in this problem. And all we need for that is the definition of stress. We want to calculate the stress is force over area. So the maximum stress is the maximum force over the area. And the maximum force is determined by the maximum weight of the elevator. So this way we can calculate the unknown maximum weight of the elevator. It's the little m's here, knowing the maximum stress or the maximum force. And so I rearranged this equation here. I rearranged it for this maximum mass of the elevator. It's the maximum stress, which makes sense. The bigger the maximum stress, right, the bigger the mass of the elevator and occupants could be. And it also depends on the diameter of the cable. And then it depends on inversely on the acceleration of gravity and the acceleration. So if you had your elevator on Saturn where the acceleration of gravity is much larger, it's much more likely to snap because it's overcoming a bigger weight. If it's on the moon, if we put this elevator on the moon where the acceleration of gravity is smaller, then it's much less likely to snap because you're overcoming less weight on the moon. But anyway, all these numbers over here on the right, we know. I can plug them all in. I did this here. 20,000 kilograms. 20,000 kilograms, that mine elevator would snap on you. And so you do have to be careful about the mine elevator and what you fill the mine elevator with. You know, if you go in Patterson office tower and you go in the elevator, I'm very conscious of this now. It says maximum number of occupants. It doesn't say that because they just don't want us to get too close to one another. It says that because they're worried about the maximum weight of the elevator and the occupants. Anyway, that's the end of today's class. Sorry, I've gone on a minute too late. Next class, fantastic stuff, actually. It's hydrodynamics and it's hydrostatics, and it's like water and air. It's all about water and air. And it's in these classes that we're going to go from the top of the atmosphere to the bottom of the ocean.